Okay, so welcome back, and what we're going to discuss today is the introduction to what a parametric equation is. Okay, so in two-dimensional space, we're used to using the xy coordinate plane, the Cartesian coordinate plane, to describe locations of points, right? So any point on the Cartesian plane is represented by an xy coordinate, right? So, but when we deal with parametric equations, many times we deal with curves. And so we can write, for example, each of the other variables in terms of a third variable, which we call the parameter. So in many cases, we can represent a point based on this third variable, what we call the parameter. And the parameter is a variable that is dependent, is an independent variable that affects both of the x variable and the y variable. So for example, if we're looking at position, let's say we use a parameter t, which is often commonly used, and let's say t represents time. So in a lot of physical application type problems, we're interested in the position of a particle or an object with respect to time, right? So we've got this third variable, this independent variable, let's say time, and we're looking at the change in x and the change in y with respect to this third parameter t, okay? So in this case, we can represent both x and y as a function of time, okay? So let's just put this together. So if I have x, right, is some function of time, and y is some function of t, which again could be time, usually is time. And then we can represent the xy coordinate, which is a position coordinate, as what? Let's call this g. So f of t, comma, g of t. Right? Because they don't necessarily have to behave with the same function. Okay? Or what we can do is more specifically, instead of using f of t and g of t, well, we could just say x of t and y of t. We could do that, right? So basically what we're doing is we're rewriting this as a function, as both of these as functions of a third variable, what we call the parameter, okay? And so this allows us to be able to more easily describe curves, okay? For example, let's take our Earth, right? And the orbit of our Earth. So a year, right? So a year is 365.25 days, right? So if we look at 1 year, right? So for our orbit, 1 year is equal to 365.25 days, right? We have a quarter of a day in there. This is why we end up having leap year, right? Every 4 years we have to add a day, because what do? We truncate this to 365 days in a year, right? And so every 4 years, we've got to add a day to make up for the lag, okay? So again, let's just say, for argument's sake, it's 365 days a year. So, January 1st is day 1, okay? February 28th, day 59, right? And so each day of the year corresponds to a day on our calendar. So, and each day represents a position. Our Earth is going to be a position on the orbit. Okay? So let's draw this. Okay? So let's say we have our orbit. Okay? And I'm just exaggerating here. And let's say one of the foci is the sun. So the sun is located at a focus. right? So let's say that's the sun. And the other focus is, let's say, here. Okay? Again, I'm doing the best I can with my picture. And so let's say the Earth is there, right? And then as it's going around the sun, right? So here's the sun. And if it's going, as it's traveling around the sun, every day that goes by means that our Earth is somewhere along our orbit. Okay? So for example, let's say this is day 1. Let's say this is January 1st, right? So day number 1. Okay? And then let's say we go to April 2nd. And let's say we're over here. And what day is that? That's going to be day 92. Okay? And then let's say July 1st. Which is day what? 182. And then October 1st. Which is day 274. So this is t equal to 1. This would be t equal to 92. This would be t equal to 182. And this would be t equal to 274. And then, of course, after 365 days, we would be right back to where we started. Okay? Now, we can represent the position, right? So this is the orbit. So now what if I do something like this? Okay, so there's the XY coordinate system, right? So what this means is I can represent any point along this curve as an XY coordinate, but each position is dependent on time. So I can write any point along this orbit as, x of t, comma, y of t, where both x and y are functions of time. Okay? So in this case, each x coordinate is a function of time, and each y coordinate is a function of time. So that means every point on the orbit on this graph is a function, can be related as a function of time. Now, we can determine the functions for x of t and y of t, thereby what we call parametrizing the orbit of the Earth around the sun. Because again, this is all relative to the sun, right? So all of these positions we're again using the sun as a reference point. Okay, because the sun is located at 1 focus point. Okay? So the variable t is called the independent parameter, and in this context represents time relative to the beginning of the year, right? So again, t is referenced as January 1st, t equals 1, right? And a curve in the xy plane can be then represented parametrically. And the equations that are used to define the curve are called the parametric equations. Okay? And so this is what we're going for. We're going to look at how do we rewrite, or how do we parametricize the xy coordinates, and how do we find the parametric equation. Okay? So that's where we're going. Okay? So the next video, I'm going to introduce the definition of a parametric equation. And then we're going to do some more examples and go from there. Okay? Have a great day.